Yep. Good morning, everybody. Like Lucy said, I'm Nathan Studer. I'm here to talk about how we're using seL4 to secure robotic systems, particularly those written using the Robotic Operating System. But I was originally scheduled to give a talk earlier in the week, and special thanks to Hesham for switching with me while I waited for permission to actually give this presentation. But it kind of worked out because NEO this morning talked about their work with their vehicle, which was really exciting. And we're talking about a vehicle here, albeit a robotic one, and with some similar but also very different requirements than a commercial vehicle. Unfortunately, Alex will make an appearance in a video later in the slides, but none of the other authors was able to travel to me, so they'll have to just watch the YouTube video later. Agenda is pretty straightforward today. We're going to just talk about our background, our use case in particular, and then how we use the cyber retrofit approach pioneered by the HACMS project to kind of start hardening a robotic vehicle, and where we'd like to go from here, continuing to harden it. You can all probably guess what the problem is, and I don't need to convince the people in this room that any system could use more security, regardless, especially robotic systems, even small ones. If you don't think a Roomba could hurt you, you don't own a cat. If it ended up underfoot at the right moment and you fell down the stairs, you would be just as hurt as if the T-1000 appeared and was to attack you. So even small robotic systems could use some better security. But in our case, we're talking about a vehicle. Sorry. Okay, sorry about that, guys. And a unique aspect of ground vehicles is that a lot of the talks here and a lot of work in the past were very concerned about people coming in over the wireless link, which we are concerned about with ground vehicles. But like with a quadcopter, you don't really need to worry about somebody leaping onto the quadcopter and then attempting to get access to any of the physical ports. Whereas with a ground vehicle, somebody could conceivably do that. So we do at least need to try and have some protection against that type of attack. Especially in our case, because a human driver does provide some cybersecurity. If you don't believe me, go out and try, open somebody's car door out there, try to get access to their radio. They will punch you. They will call the police. They are providing some cybersecurity protection. But now we have a robot, and the driver's not there anymore. So we need to at least be able to protect the vehicle long enough for reinforcements to arrive. So that kind of sets the stage. But first, to take a little bit of a step back, since not everybody here is probably familiar with ROS. ROS is what they call it a meta operating system. Really, it's like a framework that's meant to run on top of Unix. It provides message passing, some basic services, and functionality so that you can do distributed development and distributed execution of robotic systems, kind of like the example shown here. And this loose coupled framework is really what gives ROS all its power, and it kind of is focused on code reuse. And you can go out right now to the ROS community and just pull down ROS components, and you can quickly put together a robotic application for all sorts of different robotic platforms, which is really, really cool and is why it gets used so much. The messaging layer bears special attention. For ROS 1, it was something different, but we're more focused on ROS 2, which uses DDS, which is the data distribution service. Important thing is it's a publish-subscribe multicast mechanism, and that's really what underpins a lot of ROS. And it also has some really cool functionality like DDS security, which we can use to kind of harden the communication in the system. So with kind of that background in mind, our project goals were, of course, we want to improve the security of robotic systems. But some additional side goals kind of pop out of that. ROS, as I kind of alluded to, was originally intended for use on Unix systems. Not everybody runs Unix for everything. So being able to run ROS in a constrained environment like seL4 can help to bring ROS to more platforms. And then ROS is used in all kinds of academic and commercial applications. So being able to run ROS applications directly on seL4 is a really good way to get in the door when those groups figure out that they actually do need more security than what Linux is offering them. Anyone who's done work with a robotic system or autonomous vehicle is going to have to forgive me how much I'm simplifying things here. But this is like a very simple picture. It's not quite as simple as what the proof engineer showed the other day, but this could be some very simple requirements for our robot. We want to be able to do over-the-air updates of it. I won't really get into that too much here. We would like to have teleoperation, have somebody drive the vehicle from remotely. We want to have some kind of autonomy functionality because we don't want to always have somebody teleoperating it. But for those of you that aren't familiar, autonomy stacks are usually very big, very complex. They might have some security vulnerabilities that we don't know about, so we need to be able to protect against that. And then since it's a vehicle, there are going to be some safety requirements. Just for one example, in our application, it's a very simple example. There are other requirements, but there is a light. The light is one color when the vehicle's in autonomous mode. It's a different color when it's being teleoperated, and it's another color when there's a human driver. And that light just gives an indication to people around it that the vehicle might start moving, even if there's a driver not in the seat. So it's really important that that light reflect the state of the vehicle, even if somebody's attempting to break in over the wireless network. So with those requirements in mind, we could go out into the community, grab a bunch of ROS nodes, and put together an example of robotic vehicle using some of those ROS nodes. Like we could grab an autonomy node, we could grab a teleop node, we could grab the safety light node, put them all together, run them on top of Linux. And with our robot system, we have a bunch of I/O. Well, we have the camera for vision. We have the radio providing the connection to the operator. We have the connection to the CAN bus in order to talk to the other ECUs in the system. And then this thing, the VIC, is a vehicle controller that we connect to over a network interface, and that's what we can use to move the vehicle around. Once again, very, very simplified picture. The real architecture is way more complicated, has multiple computers in it, but just for the sake of this presentation, trying to keep it pretty easy. And another important thing to mention here is that Chris and Leia got up here before and mentioned and said how important x86 was to us. They are working on different projects than I am, and this one also is an x86 computer. We love ARM, we love RISC-V, we have lots of customers that use them, but when computing performance is important, they tend to pick x86 still, even if we prefer they do something else. So we have to be able to support that. So even with this simple architecture, some security requirements kind of immediately come to mind. We want to detect, we want to prevent a number of the usual attacks. We want to be able to harden the communication some. And then in our case, one of our more interesting requirements, which is somewhat security, somewhat functional, somewhat safety all combined, is that if a vehicle is compromised, we want to get it back somehow. We don't want somebody to be able to just hijack it and drive it off. We want to get it back. Which makes things a little bit more interesting. It's important to note that I think Gernot might have said this in his presentation, is that none of these requirements is something seL4 can do alone. It requires really good system design to actually be able to prevent these type of things. But seL4 can play its part. So in our case, we came onto the project and we started using the cyber retrofit approach to take the application that I kind of showed earlier and lift it into a virtual machine and start picking pieces off to run directly on seL4, resulting in kind of an initial architecture like this. And really just taking that application and putting in the VM did give us some immediate security benefits because this board has many ports on it that aren't used but are potentially exposed. So before, when they were just running Linux, those ports could potentially be used against us. In this case, they're now kind of hidden from the virtual machine, so we at least have some protection there. Moving some components over to seL4 natively, we chose to start with the radio, and you can see we put it on its own network connection, ran it through a firewall before connecting it to the virtual switch in the system. We also added a network monitor to watch the virtual switch, just to try and see if it could detect any like anomalous or suspicious traffic and take some kind of action based on that. Getting to this architecture from upstream cam keys was not something that we could just do right off the bat. It did require adding some support. We had to add an I210 networking driver. We have 64 gigs of memory in the system, and we wanted to use all of it. And using that much memory with cam keys, especially handing it out to virtual machines, caused some build and runtime and performance issues that all needed to be addressed, but that Chris was able to fix. Thank you, Chris. And then from the architecture, you can see we got a lot of virtual networking going on, and past Summit presenters have talked about some of the past virtual IO net performance issues, and so we had to bring pretty much all of those fixes into our system to be able to run good enough. We did run into some interesting issues on the way. I won't get into all of them, but the first one bears some elaboration. So even though the devices were hidden from our virtual machine, when we plugged in a USB keyboard, a USB mass storage device, we'd get an IOMME fault and the system would halt, which was not expected at all. After a bit of debugging, well, a lot of debugging honestly, what we discovered is that when the UEFI BIOS would boot, it would install a USB IRQ handler. And because seL4 wasn't overwriting that handler when we ran, that IRQ handler was still resident. And when someone plugged in a device, it would run, attempted to EMA transfer, which would get blocked as intended, but then the system would halt, which was obviously not intended. So we did have to make some improvements to how the IMMU faults were handled to prevent the halt, but we also updated the bootloader to just disable all the extra USB devices as an extra kind of means of protection. But even with this initial kind of very bare minimum cyber retrofit approach, along with some really good system engineering from the rest of the team, we were pretty successful. We took the vehicle out on a field, drove it around, and we let a red team have access to it, both wireless and some time-limited physical access to it, and they were unsuccessful in breaking into the vehicle. That's not to say that they couldn't have found a way in if we had given them more time, and there are still some very big concerns with this architecture. Like I said earlier, the autonomy stack might have some problems with it, and it's running right alongside the same software that controls the vehicle. Anyone familiar with the Chrysler hack from a decade ago now knows that giving a direct CAN bus access to anything is a terrible, terrible idea. So this was really good as a first pass to get things up and running on seL4, but this is not the architecture we want to go with. We'd really want to move to something that has that functionality off and running in a more trusted environment. So kind of an architecture like this, with the teleoperation and control running directly on seL4. And kind of a cool thing with this architecture is it does solve some of those security issues, and at the same time, it gives us a way to get the vehicle back if the VM was to go down. Because if the vehicle went down, the VM crashed, which is the main source of our untrusted functionality. If it went down, we still have the nodes that are responsible for actually driving the vehicle. So we could have somebody come in over the radio and drive it around, get it back to the garage, or do some kind of waypoint backtracking. So we have a lot of options there that we could potentially get the vehicle back, which is a cool side effect of kind of shoring up the security. But getting to this architecture has had some issues in our case because we don't have some of these pieces. CAN is just a driver. That's pretty simple to shore up. But then ROS, there have been presentations in the past on, well, it'd be really cool to run ROS on seL4, but to our knowledge, nobody's actually done it yet. There has been a port of a DDS library to seL4. It's not readily available to commercial companies. So in our case, we're a commercial company. And our customer also didn't want to use anything that was proprietary restricted. They wanted to have rights at the end of the day. So we weren't able to use that. So these were the two gaps that we really needed to address. So to address these, we decided to do a second cyber retrofit round and follow kind of the same process. And we took a system using a virtual machine running a ROS application. We ported DDS to seL4, ported ROS to seL4, and then once that support was in place, started to pick off functionality out of the virtual machine and run it on top of seL4 directly. To see a picture of kind of what our reference system looks like, once again, very simple. We just kind of had needed some place to start. We picked a node that kind of represented the kind of operations we might expect in a robot, like teleoperation, logging, a joystick, and we ran those in a virtual machine. And this was all connected to a simulator to do the testing. Theoretically, the simulator behaves just like the vehicle, so if you can run it in the simulator, you can also run it on the vehicle, but it's much easier to run in the simulator and much less dangerous if you can run it on the simulator as well. If we compare seL4 to ROS, we can see what some of the issues we're expecting to run into pretty much immediately. Thankfully, a lot of work has been done with seL4's networking support, that it's pretty top-notch at this point, so that we weren't concerned there. ROS is really meant to be dynamic, but like Gernot said in his presentation, in our case, we could just simplify everything to a static system. Didn't really need to worry about that. DDS I kind of talked about, but the big one is that ROS is mostly written in C++, using the C++ standard template library, which we're a small team and we had a very small budget, was not something we were probably going to tackle as part of this project. So that was definitely a big concern. Luckily, there is a version of ROS called micro ROS that is written primarily in C, so that was a pretty obvious choice to start there, and so that's where we focused on. But micro ROS does still require DDS, so we needed to get the DDS library as well. So we went out looking to what the usual DDS libraries in use are, and here's kind of the most popular ones right here. We're not going to go over everything in this list, but it was a pretty easy choice because the most popular ones require C++ once again, and only a couple really only use C, and only one had all the functionality we really wanted. But because and especially because it had socket support, we were able to really quickly, with some trouble, patch it into the Pico TCP socket layer, and then we had a DDS library running on top of seL4. And from that, it was pretty easy to just port micro ROS. I should mention first that there are other DDS candidates out there. There are a lot of them. Some of them we just didn't have time to look at. The ROS DDS library is especially interesting to us. We'd like to look at that in the future. But then some of the more popular ones that come up from time to time, we kind of dismissed them right away because they were proprietary and they had an expensive license, which would have just broken our budget on this project. Getting back to micro ROS, most of our issues with micro ROS were to do with C++. There was still some C++ STL code in the system, but we were able to convert that to C or just ignore that particular library. But the build system was a little tricky to get to work. It uses a custom CMake build system. seL4 cam keys uses a custom CMake build system. It seems like it'd be easy to stick those two together, but it was not. It was not at all. Eventually, we managed to figure out a way to have the cam keys build system call out to the ROS build system, package it as a static library, and then link all that back into seL4. But it was not easy. And most of the issues are because the cam keys build system kind of includes so much extra stuff when building components that there's just lots of really weird conflicts. And this is where we think moving to MicroKit in the future is going to be very helpful, is because that build system is a lot more isolated when you're building the individual components. But with that micro ROS ported and DDS ported, we were able to move most of the ROS functionality out and run it directly on seL4, which in this video in the next slide, Alex will demonstrate using the simulated system.
All right, here we have our ROS on seL4 demo set up. Here we have a ruggedized x86 PC, which is running our ROS and seL4 software on top of it. And it communicates via Ethernet here to our host PC. Our host PC is running a simulation environment with a simulated vehicle. The ruggedized PC will send ROS messages through the Ethernet to the simulation environment, and the simulation environment will also send messages back through the Ethernet to the ruggedized PC. You can also see here that on the host PC we have a serial terminal open that connects to the serial output from the ruggedized PC in order to see messages such as the seL4 serial messages, as well as the ROS node serial prints that we see. So here we can go ahead and control the vehicle using the Xbox controller, which is connected via USB to the ruggedized PC. To enable motion, we hold down the bumper, and then in order to shift the gears into drive mode, we press the A button. And once we do that, we can use the joystick to control the vehicle. And here you can see the vehicle is moving with the joystick controls. And if we pop on over to the host PC, you can see that a bunch of prints from the ROS pose node that we had running on top of the ruggedized PC are printing out the current position as well as the predicted position of the simulated vehicle from the environment. And that is our ROS on seL4 demo.
Yeah, thanks, Alex, for providing the video. I mean, it looks like a video game there, but it is running ROS, and it is much cooler on the real vehicle, but unfortunately that's not something that we have permission to show. Of course, this is just running a very basic ROS nodes on seL4 right now, very basic. We need to add a lot more functionality in order to run real ROS nodes like you would find in a very advanced robotic system. And some of the gaps are listed here, and it's been very exciting at this summit hearing how the various attendees have kind of already tackled some of these. So we're definitely looking forward to some of those developments to potentially bring them in, especially the NEO's presentation where I saw libc++ pop up, because C++ support is really the big one that's holding us back in this case. And that's partially internally, we're not sure that running C++ on a microkernel like seL4 is the right approach, but the customer has said all ROS nodes must be written in C++. So it kind of doesn't matter whether or not we philosophically agree with them. We kind of have to figure out a way to support what they're asking for. So the future work is really trying to get the stuff we've done so far out into the community, and so that other people can take advantage of it. We need to be able to improve the DDS work we've done so far by adding security support, improving the performance, things like that. We want to switch to MicroKit. We want to add additional I/O to the system, run on other architectures other than x86. And then as I was going through the presentation, you might have looked at the network bridge and gone, oh my goodness, they are putting a lot of faith in that one component to route traffic where it needs to go. And we are well aware of that. And we want to do something about that. And so we're working with some of the members of the community to try and figure out a way to build up assurance argument of at least that particular piece of the system for the time being. So in conclusion, I mean, the cyber retrofit approach that we've shown, that others have shown here, it works. It was a great innovation as part of the HACMS program, and it's a really good way to get in the door with a customer that already has a developed system and start adding security to it. And with just a little bit of work, we were able to add ROS support to run natively on seL4. But unfortunately, there's still a lot of work needed to get all the way to being able to run a full robotic system on top of native seL4. And with that, I'll take any questions.
Time for a couple questions.
The probably obvious question, when will this be released publicly?
That is a good question. We are putting in our request, and it will be 2 weeks to 2 years probably, given past experience.
What are the possibilities for getting micro ROS to actually explicitly support seL4, because they do support various RTOSs already? So is there any benefit in pushing that back to the micro ROS community so they can make that building block generically available?
So the question was if we were going to push our work back to the micro ROS community. And that's not something we really have thought about yet, but definitely if we're pushing things out, that would be a good idea. Thanks for the suggestion.
I'll just get the speakers to switch laptops, please.